Hi guys, and welcome to the video on theoretical versus experimental probability. So in this video, guys, we're going to go over calculating probability as a percentage. Probability is all around us, and it's important to understand how to interpret it or calculate it. That's why we're doing this. One of the main things is that probability and statistics are used in a daily basis when we talk about things like even the weather. And so it's important to be able to understand things like that. And you'll know you're successful when you can calculate the probability of a task like drawing a certain card from a deck or something like, very, very basic like that. Okay, so starting first with theoretical probability. The theoretical probability of an event happening is the total number of favorable outcomes that you're looking for divided by the total number of outcomes that are possible. And really, that's it. So just remember, though, that theoretical probability is the probability of an event happening in theory. Okay. The no trials have actually been done. We are simply calculating what we expect to happen. The experimental probability, the actuality of an event happening in repeated trials, is calculated using the equation below. So the probability of that event is the number of times that event actually occurred divided by the total number of trials that were conducted. So here's a handy chart for you guys. Um, you can pause the video here to kind of note down the difference between the two of them. The formulas are kind of the same, but there's a pretty good example of how the two are different in something such as a coin flip. Theoretical probability would be if you toss a coin once, what do you expect to happen? The experimental probability is you tossed it multiple times. And what did you actually see happen? So, the complement. When we talk about probability of an event, we must also consider the idea that the event will not happen. This is called the complement. We're not talking about being nice, okay, guys? The probability of an event and its complement must add up to 100%. So I've got P plus P with a little apostrophe called P naught equals 100%. This must always be true. So, example, there is a 38% chance that it will rain today, means there is a 62% chance that it will not rain today, because 38% plus 62% is 100%. Okay, that kind of transitions into probability versus likelihood. An event's probability indicates its likelihood of happening. The closer to 100%, the more certain it is that the event will happen. So I have a range of probabilities here and how you would how that would turn into likelihood. So 0%, like no chance. An example would be a cat will give birth to a rhinoceros. That's just not going to happen. It's impossible. A low chance would be something like it will snow in the Sahara. It is possible. It's extremely unlikely, but it is possible. An even chance would be a 50-50. If I toss a coin, it will land heads up. And a high chance it will snow in Austria. Austria is a European nation, and it very likely will snow there, just like it very likely will snow in Wisconsin during the winter. And then there are certain events that will happen no matter what, such as it will get dark tonight. At some point, it will get dark tonight. So that is a certainty, and it will happen. If an event's probability is close to zero, that event has no chance that it will happen. So we're talking at like a 0% chance, or you're starting to get like 1 to 2%. 1 to 2% could happen, but they're incredibly unlikely to happen. So, an example of this is that the weather anchor declares on the news there is a 35% chance that it will snow tomorrow. How likely is this event to occur? So, if I look back at the previous page here, 35% would be right about here. There's a low to even chance that it will occur. But if you were going to hedge a bet, if you were going to make a bet here, you would still probably bet that it is not going to snow tomorrow. That would be the more likely outcome. So I'm just going to note that here. The more likely outcome to not, is that it will not snow. Okay. Moving on. Simple probability. Remember that we can calculate the probability of an event happening by dividing the outcomes we are interested in, not necessarily the ones we want, by the number of possible outcomes. Then you can also use a series of recorded trials to calculate experimental probability. So examples of simple probability would be drawing a card from a deck, and does it turn up a certain color, or does it turn up a certain way, such as like does it turn up as a 2 or does it turn up as a king? Rolling a die, usually we're talking about a 6-sided die here, a die that you would roll labeled 1 to 6. Flipping a coin, coins can come up one of two ways, heads or tails. And spinning a roulette wheel. So depending on the number of sections that a roulette wheel has, or spinning a spinner or something like that, that would alter the probability of that event. So we're going to start with an easy one, okay? I roll a d6. That's a common abbreviation for 6-sided die. How many equally likely outcomes are there? So again, 6-sided die, 6. How many equally likely outcomes are there? 6. This is the bottom of the probability fraction. So this is what you consider when you start talking about the bottom of or your total chances. How many equally likely outcomes are there? This 6 is the total number of equally likely outcomes. So with that in mind, what is the probability that I roll a 4? So remembering the formula, that probability is equal to one outcome over the total outcomes. Okay. Then that would mean I have a single chance because a 4 is one outcome and there are 6 possibilities. So the probability of that event happening is 1/6, which is approximately 16%, 16.66%. So moving on to a different example, if I draw a card from a deck, then how many equally likely outcomes are there? If you consider, okay, if you think back to your knowledge of decks of cards, there are 52 different cards, which means drawing a specific card means there are 52 outcomes. So that said, what is the probability that the card is a 2? There are 4 different colors, or 4 different suits, excuse me, guys. You've got your clubs, you've got your hearts, you've got your spades, and you've got your diamonds. And the thing about all of these suits is each one has a 2. Each has, my H got covered up. Each has a 2 in it, which means, that implies, there are 4 2s in the deck. So I could draw any one of these 4 2s, and that would satisfy the requirement that the card is a 2. So there are 4 2s out of 52 chances. So the probability here is 4 out of 52, which reduces to 1/13. So the probability is about 1/13, 1/13th, that I draw a 2 out of a deck of cards. So I'm just going to rapid fire through some examples really quick. What is the probability of choosing a king from a standard deck of cards? And so standard deck of cards just means the regular old 52. So probability of choosing a king, just like we saw before, any particular card, there are 4 copies of it in a deck, one of each color, and there would be 52 total cards in the deck. And then that probability is 1 over 13 when you reduce it. What is the probability of choosing a green marble from a bag that contains 5 red, 6 green, and 4 blue? So that means there are a total of 15 marbles. So there is a total of 15 marbles. And I got that by adding up the 4, the 6, and the 5 to get my total. So that will be the bottom of my probability fraction. I can already put that down. On the top, I'm going to put the total number of green marbles. So there are 6 of them. So then my fraction reduces to, both these are divisible by 3, 2/5. So there is a 2 in 5. I want to fix my fraction bar. There is a 2 in 5 chance of drawing a green marble. So put a check. Ooh, that's an ugly looking check. I was just going to try to put a check mark for my completed answer and check mark for my complete answer. What is the probability of choosing a marble that is not blue from problem 2? So if I go back and I remember what was said earlier in this lesson, the probability of an event plus its complement has to equal 100%. So the probability of drawing a blue marble is 4 out of 15. The total number of marbles, 100%, would be 15 out of 15. So if I have to calculate the probability of choosing a marble that is not blue, it would be blank out of 15. And the number that is on the top here, x out of 15, needs to be the number that 15 minus 4 is in order to add up to 15 when added together. So 4 plus x equals 15. So really simple algebra problem. And I can calculate that x is 11. 11 out of 11. So then the probability of that, the probability of not drawing a blue, would be 11 out of 15. And then, so what is the probability of getting an odd number when rolling a d6? So let's consider, okay, the possible outcomes for a d6. I can get a 1, I could get a 2, I could get a 3, I could get a 4, I could get a 5, and I can get a 6 for a total of 6 outcomes. So the probability is out of 6 outcomes. I can have a 1, that'll work, a 3, and a 5. Meaning 3 out of the 6 outcomes are outcomes that I care about, which would reduce to a probability of 1/2. And then an experiment was done and a 6-sided die was rolled 100 times. The results were recorded below. So I have outcome and frequency here. So what was the probability of rolling a 3 according to the table? So 100 trials were done. So this was 100 trials, which means this is going to be the bottom of my fractions. These are going to be the bottom of my probability fractions here. Bottom of fraction. So, what was the probability of rolling a 3 according to the table? I'm going to look at the table for 3s. The outcome 3 had 22. So there was a 22, fix my 2 here, out of 100, which would be about 22%. What was the expected probability of rolling a 3? So when they say expected probability, they're asking you to shift back to theoretical. Okay, the top one, the top equation, or the top number, letter A that I was doing here, that was experimental. This is an experimental probability problem here. Up here, letter A is. Letter B is theoretical again. So on the die, okay, there are, in theory, 6 outcomes that could happen. Exactly 6. 6 unique outcomes. And then there is 1 that satisfies the criteria of rolling a 3. So the probability is 1 over 6. What was the probability of rolling a number less than 3 according to the table? So numbers less than 3 here, if I erase the arrow, would be a 2 and a 3 that satisfy the criteria. So you have 16 plus 20, because both of those satisfy the criteria, over 100. So the probability is going to be 36 over 100, and that leaves you with a probability of about 36%. You could reduce your fraction to 36 over 100, down all the way to 18 over 50, and then you could do it again to be 9 over 25. And then, so what was the probability of rolling a 3 or a 5 according to the table? So in scenarios like this, you have a 3 and then you have a 5 here. So I've got a 22 plus an 18 over 100. So that gives me a 40 over 100, or a 40%. So I'm going to just move up 40%. Okay, so in summary, guys, theoretical probability is the probability of an event happening according to what we expect to happen mathematically. Experimental probability is the probability found by repeating a trial and recording the outcomes. And so what we kind of saw that highlighted in is the early examples, like the first two examples were theoretical probability, and the third example with the table, that was experimental probability, because it was the probability of an event happening over and over again, and then how many actually showed up that way in the trial. And then, so remember what complement and likelihood mean too. Complement being the probability of an event not happening, and then likelihood is kind of translating that probability into real world understanding. So that's it for today's lesson, guys. Thanks for watching, and I'll see you in the next video.